In this video, we're going to talk about constructing a confidence interval to estimate a population mean. All right. In order for us to get these confidence intervals, right, that's going to be the main focus of this video. We need to review the mean of the sampling distribution of the sample mean and the standard deviation of the sampling distribution of the sample mean, right? As we've stated before, remember a sampling distribution is a distribution of a statistic. And in this case, we're going to be talking about the sample mean. And so we said that the mean of that sampling distribution, remember we notate that mu sub x, it equals the population mean, right? So this right here is the population mean. Okay. The standard deviation, also called the standard error, I'm sorry about that this thing is writing this way, but the standard error or the standard deviation of the sampling distribution of the sample mean is given by sigma with a subscript x bar, kind of like mu is this population mean. When we put a subscript to say it's the mean of the sampling distribution, it is the population sigma, or standard deviation, divided by the square root of n. And that is our standard error, standard deviation of the sampling distribution. With those two things, we can get a good idea of the actual general form of a confidence interval. Remember, your confidence intervals always involve your point estimate, plus or minus the margin of error. Margin of error, right? And so remember, we add and subtract the margin of error. Remember, your margin of error is your confidence coefficient times the standard error. Okay, and so what we're going to talk about is how we can develop the actual, we're going to talk about what the confidence coefficient is when we're doing a confidence interval for the population mean. And we're also going to talk about what happens with this standard error here that we generally want to put here for our standard error. Okay, and so let's continue. All right, when we construct a confidence interval for a population mean, there are two different approaches, all right? And it's going to depend on whether we know the actual population standard deviation, sigma, or if we do not know the population standard deviation, sigma. So those are supposed to be sigma symbols. When we know the population standard deviation, which is very rare, right? This situation here is very rare. Very rare, right? The confidence coefficient will be a z statistic or a z value, right? Remember, your z comes from your standard normal distribution. It's the bell-shaped distribution. All right, that's a poor bell-shaped distribution, but it's centered at 0. It has a standard deviation of 1, right? And so we know that most of our observations are within 3 standard deviations from the mean, the population mean, which is 0 for our standard normal curve, right? It's a z value, and we can use our z table, and that's going to be our confidence coefficient. So everything that we knew before, right? For instance, when we did a 90% confidence interval, we use z equals 1.645. That's a 4, not a 9. When we did a 95% confidence interval, we had 1.96, and then a 99% confidence interval, we had 2.58 as our confidence coefficient, right? And that's basically dependent on what percentage in the middle of our normal distribution we want it to be confident in. That is what we're going to use for our confidence intervals for our population mean when we know sigma. This case right here, case 1. When we do not know sigma, the confidence coefficient will be a t-value. All right, and we got to talk about what a t-value is. It is related to a z-value, but it is a t-value, right? It comes from a totally different distribution, and that distribution is called the t-distribution. Almost like standard normal distribution, sometimes we say it's the z distribution. So let's go and talk about or discuss some of the facts about the T distribution. For one, the T distribution is a bell-shaped distribution. It is still bell-shaped, all right? Just like the normal distribution. The difference is that it has thicker tails. And so where the tails on this distribution are close to our horizontal axis here, all right, it's not kind of symmetric. The T distribution is going to have thicker tails, meaning the tails are going to be a little higher compared to our normal distribution, okay? That is one fact about the T distribution. It is centered and symmetric at 0, right? Because it is bell-shaped, it is symmetric, and its center is also at 0. And because it has thicker tails, there's a little bit more variability in this distribution compared to the normal distribution. And so it has a slightly larger standard deviation than the standard normal distribution, right? It has more variability. All right. Now, when we first talked about normal distributions, we said that there are multiple normal distributions, right? Men's heights, the height of men in feet, or sorry, in inches, is a normal random variable. It's normally distributed with its own mean and standard deviation, right? Of course, women's heights, their distribution is going to be a normal distribution as well. They have different heights, right? And so there are multiple normal distributions that we have for different variables, whatever we're studying. But all of those normal distributions can be standardized into our Z distribution, and that's why we always focus on the Z values in that Z table, that standard normal table. Well, it just so happens that the T distribution doesn't work specifically that way. The T distribution depends on what we call degrees of freedom. All right. And a degree of freedom is basically the sample size minus 1. That's what we're going to classify as the degrees of freedom. It is defined as the sample size minus 1. And in all of our studies, our sample size is usually n. And so if I subtract 1 from n, I get n minus 1. And so if you want a formula for degrees of freedom, it is n minus 1. That is the number of free values that are that can be estimated if you know the sample mean. But that's degrees of freedom. Because the degrees of freedom can change depending on our sample size, which is n, there is a different T distribution. I'm going to abbreviate that with DISTR for each degree of freedom, right? So we can come up with a bunch of bell-shaped curves that depends on this n minus 1 degrees of freedom, all right? One of the things that relates these is it is bell-shaped, but it has thicker tails, all right? The thing that relates this distribution to the Z distribution is that as the degrees of freedom increases, the T distribution gets close to the Z distribution. It becomes standard normal. Okay, the Z distribution gets close to normal, right? And so as n approaches infinity, all right, or if n equals infinity, then the T equals the Z. Okay, so that's a couple of bits of information about the T distribution. Again, it is a bell-shaped distribution. It just has wider tails. And just like with the normal distribution or the Z distribution, we can calculate probabilities, right? I can find the probability of this, but I'm going to have to use a table, right? And so I can go to the table, and this is not a Z, this is now a T. That depends on this degrees of freedom. Degrees of freedom, we usually abbreviate with the word, the letters DF for degrees and freedom. And we can use that table to help us see the probabilities associated with certain values of T, okay? So now what we're going to do is we're going to talk about, now that we know the confidence coefficient for when we know the population standard deviation, we're going to use a Z. And when we don't know the population standard deviation, we know that we're going to use a T, okay? So let's talk about the actual confidence interval. If I can click. And so the formula for the confidence coefficient for a population mean when sigma sub x bar is unknown, I'm going to take out that. I'm going to say when sigma is unknown. All right, that's the population standard deviation. I'm going to abbreviate that with SD. So it's just a sigma, or you sometimes see it written as sigma sub x. When I have that x bar there, it's saying the standard deviation or the standard error of the sampling distribution of the sample mean, right? And so that's actually an error. So my confidence interval, again, it's the point estimate. We already talked about that, so I'm not going to rewrite it here. I will just go ahead and actually say it. It's our point estimate. The point estimate for a population mean is your sample mean. So it's going to be x bar plus or minus our confidence coefficient. When sigma is unknown, it is a t that depends on our degrees of freedom. And it's going to be multiplied by our standard error, which is sigma over the square root of n. Now, this is unknown, right? And so what we do in practice is we use the sample standard deviation as an approximation for that sigma, which is the population standard deviation. So we use S, and that looks very weird. So we use S, I'm going to use a cursive S, to estimate sigma. And so our real confidence interval is going to be coming from x bar plus or minus t times s over the square root of n, right? And so this is an approximation for our sigma, our population standard deviation, okay? If sigma were known, again, that can be sigma sub x. I mean, it really and truly, it can be thought of as sigma of x bar, because if I don't know sigma, then I don't know this whole thing here, right? And so I guess it's not really an error. But if sigma were known, we would use a z right here instead of a t, right? And again, if sigma, that's your population standard deviation, okay? Most of the time, we don't know that because we don't have access to our population, okay? And again, the reason why we use a t, because there is variability added. There's additional variability added into our confidence interval when we use this as an approximation for our sigma here, all right? And so we can no longer use a z here. We have to use t so that it can add some variability to our distribution, our sampling distribution, okay? And so now that we know that information, we're at a good point to talk about when we can and when we cannot use this confidence interval. In other words, what are the assumptions, are the qualifications for projects to use this distribution? And all right, so these are the assumptions. All right, our data must be obtained by randomization, right? Anytime we use anything related to the sampling distribution of the sampling mean, we got to have randomization. So a simple random sample or random sample is great in the wording or the setup or the design of the study to let your sample do through randomization. If this is not true, then your sample may not be representative, things may not be independent, and your results are going to be tentative. Okay. What we also need is we need that bell-shaped characteristic to go on, right? And so our population distribution should be approximately bell-shaped or normal. Now, by the central limit theorem, this will be the case as long as your sample size is large, right? And when we say large, by way of the central limit theorem, we know that n has to be greater than or equal to 30. All right. So if our population is not normally distributed, we need n to be greater than or equal to 30. That's a 30. Or we need to know that our population distribution is normal. And so once those two characteristics are satisfied, then we're at the point where we can go ahead and proceed with constructing this confidence interval. And so we're going to look at an example of constructing this confidence interval. Example 1. Suppose a random sample of 81 students from the University of South Carolina was taken. Among the sampled students, the sample mean number of times they used the word like in a 5-minute conversation was 13 times, with a sample standard deviation of 2. Construct a 95% confidence interval for the population mean number of times USC students use the word like within 5-minute conversations, right? And so the first thing I'm going to do is I'm going to check my assumptions, right? So let's check assumptions. All right. Because it says a random sample here, I know that I satisfy the assumption of randomization. So that checks off, right? There is nothing in this write-up, this scenario, that says that my population is normally distributed, right? I'm given the sample mean number of times that they say like in a sentence or in a 5-minute conversation is 13 times. And I'm also given the sample standard deviation, which is 2. Okay. I don't know how the population distribution is distributed. I don't know if it's normal or not, but I do know that my sample size is n equals 81, right? That is greater than or equal to 30. So by the central limit theorem, all right, the sampling distribution of the sample mean is approximately normal, all right? So I'm going to write that. I know it's going to look weird with this typing or this writing here. So the sampling distribution of the sample mean is bell-shaped. And once that is the case, then I can use a bell-shaped sampling distribution or our T distribution or our Z distribution in order to help me come up with my confidence coefficient, okay? Once we have that, we're ready to construct the 95% confidence interval. This confidence interval requires us to have X bar plus or minus, all right? We're either going to use a T or a Z here, right? T or Z, all right? We use T when sigma is unknown, and we use Z when sigma, the population standard deviation, is known, right? And so if I read this, the only standard deviation that I'm given is our sample standard deviation. And so since we're only given the sample standard deviation, I'm going to use a T as my confidence coefficient instead of a Z. And so the last part of my confidence interval is to multiply this T by the standard error, which, since we don't know sigma, is S divided by the square root of N. Okay? And so we can pick out these values or determine what these values are by using a table and using the information that's in the problem, right? For instance, it's given to us that X bar is 13, S is 2, N is 81. But what about T? Okay. Well, T depends on degrees of freedom. Remember, degrees of freedom equals N minus 1. Our N here is 81. 81 minus 1 is 80. Okay. So the degrees of freedom here, this is a minus and a 1, is 80. So how do we find this V here? There are a couple of ways. You can use technology or you can use a table. In your textbook, and I'll also give you this table here, we have a T distribution, right? Table B, T distribution critical values, okay? So what this table does is it gives the right tail probability. Remember when we were dealing with the normal distribution, the Z table, it gave the left tail probability, the proportion below, okay? So this distribution is different. The degrees of freedom, which I have been talking about, is listed in this first column. Notice we have the degrees of freedom from 1 up until 30. Then it starts to count by 10, 40, 50, 60, it skips over 70, 80, 100, and then infinity. Okay? 80 is the degrees of freedom of the actual example that we have here, right? And so this is going to be, this row of numbers is going to be very important for us, okay? So we need the t-value, and this is what this table gives. Now, the normal distribution has your z-values on that column and that top row, that first column and the top row. It has your z-values, and within the table, in the middle of the table, it has probabilities. This table is totally different. This is a table full of t-values. All of these numbers in the middle of this table are t-values, those confidence coefficients. No probabilities are in this table. The probabilities are kind of given as these subscripts on this t-value here, okay? And so let's see how these work. Remember that we're doing a 95% confidence interval, all right? That means I'm going to go back to this page here, right? We're going to do a 95% confidence interval, 95%. All right? So we want 95% of our observations to be in the center, right? So this is our center. When we say 95% confidence interval, we want means that are in this area right here, 0.95. That means the tails of this distribution add up to 0.05, and that'll give us the whole 100%, or the whole 1, right? So this area here with that area there, they add up to 0.05, right? Since this is symmetric, if I divide 0.05 by 2, that means this area is 0.025, and this area here is 0.025, right? So that's the probability here of 0.025, and this red probability here on the area under that curve is 0.025. What this table does is it gives you the amount above, right? And so the table is going to give us the t-value. It's going to give us the value of t that's associated, that has the area or right tail probability of 0.025, okay? If I go back to that table, notice here, I have 0.10. That's not the area we're looking at. I have 0.050. That's not the area we're looking at. We have 0.025. This is the t-value that we're interested in. And notice it is associated with a 95% confidence level, right? And so the way we read this is we know that we're going to be in this column to find our t, our confidence coefficient. We just have to find our degrees of freedom in the table, and it's on the row with the 80. And so our t, our confidence coefficient, is 1.990. And so I'm going to go back, and I know that t is 1.990. And I get that from this using my degrees of freedom. Okay? And so now I have everything I need to get a 95% confidence interval, right? So this is 95%, right? Confidence interval, CI. And so now I can replace these values, right? So this is going to be 13 plus or minus our t-value, which is 1.990, times s, which is 2. That's a multiplication symbol there, divided by the square root of 81. Okay? And so with that, this is a 13 here. All right. Square root of 81 is, I'm just going to say 1.99. Square root of 81 is 9. And so what we're going to end up with is, if you put this in your calculator, I believe you get 0.442178. That's 0.442178. Again, I apologize for how this is writing. If you do the subtraction, you're going to get your left or your lower limit of 12.5578. And if you do the right side, you're going to get 13.4422. Okay? And again, I apologize. This is 12.5578. And this is 13.94. Sorry, that's a 4.422. So 13.4422. And so that is our confidence interval. That is our 95% confidence interval. And so what we're going to do here is we're going to provide an interpretation. And this is going to be written a little weird because these things are not working right. I wonder if I write in cursive if it'll do better. All right. So I'm not going to try that. We are 95% confident that the mean number of times USC students use the word like within, so this is a W with a slash and an IN. I'm abbreviating the word within 5-minute conversations. Probably shouldn't be an S there. 5-minute conversations is between 12.56 and 13.44 times. So basically, since you're not going to say something a decimal number of times, it's basically going to be 13 times, right? That's a pretty small margin of error. It's not big enough. This margin of error, this 442,178, it's not enough to make a whole, right? And so it's basically saying that that mean number is pretty accurate, right? It's probably about 13 times that people, USC students, are going to say the word like within 5-minute conversations. All right. So this is our confidence interval, and this is the process that we want to go through. Okay, we're going to get back to that second example that is in your notes for this section, and so we're going to stop here in this video, and we'll get there later. Stay tuned for section 9.2.